Hello everyone. This is Diptee Dipalee Dhal from Regional Institute of Education, Mysore. Today I'll be presenting on zero-dimensional nanoparticles, which represent one of the most fundamental and fascinating classes of nanomaterials. In this presentation, I'll focus on why these particles behave so differently from the bulk materials and the main reason behind its natures. Talking about nanotechnology, it deals with the materials in the size ranging from 1 to 100 nanometers, as you can see in the picture. So at this scale, the materials stop behaving according to classical physics. And as we know that dimension is something where number of independent directions are needed to describe something. Suppose we have a big hall where you can move freely, and you have a small room, and then the movement is restricted. Then you have an ultra tiny room. Now the movement becomes very minimum. So this is the most dramatic size dependent effects which we'll be coming to know in the further discussion. So as I have given the example of room, so you can understand that what the zero dimensional nanoparticles, how does it look like? So the term zero dimensional does not mean that the particle has no size. It means that all the three directions are confined within the nanoscale, leaving no free direction for electrons motion. So as a result, the electron is trapped in all the directions. There are few examples like quantum dots, metal nanoparticles, carbon dots, and so on, which you will be coming to know in further discussions. Now, why these zero-dimensional nanoparticles are important? Think of a crowded room where there are a lot of people, so there will be strong interactions. Now, in small space, people bump into each other, and this leads to strong interactions. So, this happens in zero-dimensional nanoparticles. Then they give new behaviors, enhanced optical and electrical magnetic properties, and so on. So as you can see here, the nanoparticles are classified based on these dimensions, and I was talking about quantum dots, fullerenes and so on. These are the examples of the zero-dimensional nanoparticles 1D, 2D and 3D. Also, we can see that in the nanoscale, the size itself becoming a material property, and we'll be coming to know how does it becomes. So zero-dimensional nanoparticles are classified in following ways. First is metal nanoparticles. The examples are silver, gold, platinum, where you can think of a steel ball, which is just an analogy, which is hard, shiny, and excellent in transferring force. Next is semiconductor nanoparticles, which are nothing but quantum dots. And you can think of a rubber ball with adjustable bounds and you can squeeze it. Next is metal oxide nanoparticles, which is a ceramic or stone ball which is hard, brittle, less flexible, and it reacts with environment. It is like that. Now, carbon-based zero dimensional is nothing but fullerenes or carbon dots, and you can think of a hollow or a mesh ball which is light, hollow, and having a strong covalent bonding. Next is polymer based nanoparticles, which is soft, spongy, or a balloon ball which is flexible and can carry things inside, and it can deform without breaking. So to understand why these zero-dimensional nanoparticles behave so differently, so here we have two main reasons. One is quantum confinement effect and another is high surface to volume ratio. So let us understand what is quantum confinement. So in the nanoscale, electrons behave like waves rather than classical particles. When the size of the nanoparticle become comparable to the size of the Bohr's radius, so the electron motion is restricted in all directions, and this restriction leads to quantization of energy levels, which is known as the quantum confinement effect. So whatever I have said, now let us relate it to waves in the ocean. So we have waves in the ocean which can have any wavelength and the energy changes smoothly, almost no restriction. So this is like electrons in the bulk materials. Now imagine the waves in a small swimming pool. So only waves that fit exactly between the walls can exist. Some waves are not allowed also. And in smaller pool, we have fewer allowed waves. So this is quantum confinement, where we have fewer allowed waves and the size is limited to some certain extent. Now let us also think about a particle in a box concept, where we have the expression E equal to n square h squared square by 2 ml square. where energy is inversely proportional to L square, that is the size of the box. So as we decrease the size of the box, the energy increases. So almost as the nanoparticle becomes smaller, the energy levels become more widely spaced. So as you can see here, this is just a simulation of particle in box. And as we have discussed about the concept of energy levels, here we have the concept of band gap. In bulk semiconductors, the energy bands are continuous and the band gap is fixed. However, in this zero-dimensional nanoparticles, this band split into discrete energy levels. As a result, the effective band gap increases, as you can see in the picture, which is compared with atom, bulk semiconductor and a quantum nanostructure. So, when a nanoparticle absorbs energy, an electron is excited to the higher energy level, leaving behind a hole. And when this electron falls back and recombines with the hole, the excess energy is released as light. So, thinking of the energy level as stairs, where an electron is like a person jumping down the stairs and light is released when they land. So if we have a small nanoparticle which is having compare which we can think of a tall stairs, so electron must jump a bigger step. So a bigger jump means more energy is released, and more energy means it can correspond to a short wavelength, or which is nothing but a blue light. Similarly, if we have a larger nanoparticles, like I'll show in the picture here. So if we have a larger nanoparticles, which is nothing but short stairs, so the electron jump a smaller step, and smaller jump means less energy will be released, and less energy will correspond to longer wavelength, which is nothing but red light, as you can see in the picture. So this is nothing but comparing the energy level to the energy gap, and energy gap to size dependent optical properties. How does it show? So we can conclude that smaller particle means bigger energy jump, and it will have bluer light, and larger particle will have smaller energy jump and it will give redder light. So let us think why this doesn't happen in bulk materials. In bulk materials, stairs are so close that they look like ramp, and jumps can be of any size. So color is fixed. That's why bulk gold is yellow, always yellow. But gold nanoparticles always change color. So the second major reason for the unique behavior of the zero-dimensional nanoparticle is their high surface to volume ratio. So you can see in the picture, first picture, and I'll give you an analogy that if you have a smaller city, so most of the houses are near the boundary. And if you have a bigger city, most of the houses are deep inside. Similarly, in nanoparticles, huge fraction of atoms are at the surface. And in bulk materials, most atoms are internal. So in a tiny city, who interacts more with the outsiders? Obviously, the border houses. As particle size decreases, the volume decreases but faster than the surface area. As you can compare in the three figures of the cubes. And this results in large fraction of atoms residing on the surface rather than in the interior. So surface atoms have fewer neighboring atoms and therefore have unsatisfied broken bonds, and this leads to high surface energy and their chemical reactivity increases. So they are much reactive than the bulk particles. Nanoparticles show lower melting points, higher chemical reactivity, higher adsorption, and altered magnetic behavior because of this property. And the surface determines the overall behavior of the nanoparticle. Because of this, it also shows a catalytic property. In bulk catalyst, only surface atom participate in the reaction. In nanoparticle, a large fraction of atoms are available. This dramatically increases the catalytic efficiency and making the nanoparticles highly valuable in industrial catalysis. So after understanding the nature, the reason behind why the zero-dimensional nanoparticle behave and how does it help us, so let us understand in detail its applications. So before we had phone, TV screens, and now also we have. But before we had a fixed colors, high power use, but now we have ultra bright, sharp displays, true colors, which is nothing but quantum LED TVs, and less battery consumptions. So the smartphone you use, the smartphone screen looks better than because of this nanoparticle. Talking about the sunscreens and the cosmetics, before we had thick creams, white patches, now we have transparent sunscreens, better UV blocking, skin friendly products. And talking about the clothes, soaps, daily products, this has become antibacterial and it stays more cleaner and smell less and last longer. Talking about the medicine and healthcare, before one size fit all the drugs, means the drugs can affect all the parts of the body. Now because of this nanoparticle we have a targeted drug delivery. It helps in better cancer treatment and early disease detection and long lasting medical imaging, so people live longer and healthier lives. Talking about the toothpaste, the nanoparticles help repair tiny cracks, kill bacteria, and so on. And in transportation and materials, nanoparticles make lighter cars but stronger materials and scratch resistant paints and so on. And talking about the energies and batteries, it improves battery life, charging speed, and solar panel efficiency. So the power bank we use, it lasts longer because of this nanotechnology. And clear and water environment, nanoparticles are used in water purification filters, pollution sensors, air cleaning systems, and we have a cleaner drinking water and safer air. So these are the few applications which I have discussed in the last slide and in this also. I have noted it specifically. So nanoparticle made such a big difference. So at the nano scale, materials gain new properties that does not exist in bulk form. Gold becomes red or purple in this nanoscale, and material becomes stronger and lighter. Nanoparticle did not just improve technology, but it improved how comfortably, safely, and efficiently humans' life are. So, despite these big advantages, zero dimension nanoparticles also have some challenges like toxicity, aggregation, stability, and large scale production, which must be addressed. Current research focuses on safer synthesis methods and improved surface engineering. So, thank you for listening, and further details my friends will be explaining.